Hi guys, today we will start to talk about engineering mechanics or statics, and the statics is one of the most important courses in civil and mechanical engineering. This is the base for strength of materials, and strength of materials is a base for steel design, for concrete design, for structural analysis, and everything which you will face toward your goal to graduate. So what is mechanics? Statics is the part of mechanics, and mechanics is a study of what happens to a thing. The technical name is body when forces are applied to it. So either the body or forces can be large or small. So firstly, in the second picture, you have some wheel, and this wheel will transfer the weight or force toward this steel profile. So the force is the weight of the wheel, and the body is this steel profile, which you can notice. So this is our force, and we need to figure out what will happen to a steel profile when we are applying the force from a train into it. So there are several branches of mechanics. It can be divided mechanics of rigid bodies, mechanics of deformable bodies, and fluid mechanics. So we will cover rigid bodies, that is the things that do not change the shape, and that is what is covered in statics. And in fluids, you will face incompressible and compressible bodies, and we have deformable bodies, things that do change shape. So we have four fundamental physical quantities or dimensions in statics. The first one is length, the second one is mass, then we have time and force. So length is used to locate the position of a point in space and thereby to describe the size of a physical system. Mass will measure the quantity of matter that is used to compare the action of one body with that of another. Time is conceived as a succession of events, and force is considered as a push or pull exerted by one body on another. So statics is based on 3 Newton's law. The second one relates force is equal mass times acceleration. So this equation is used to develop systems of units, and units are arbitrary names given to the physical quantities. So we are starting with some idealization in statics in order to simplify application of the theory, and we have three important idealizations. Firstly, we are talking about particle. So particle has a mass, but a size that can be neglected. For example, we have the size of the Earth is insignificant compared to the size of its orbit, and therefore the Earth can be modeled as a particle when studying its orbital motion. When a body is idealized as a particle, the principle of mechanics reduced to a rather simplified form, since the geometry of the body will not be involved in the analysis of the problem. So we have here one example. Three forces act on the ring. Since these forces all meet at a point, then for any force analysis, we can assume the ring to be represented as a particle. So rigid body. Rigid body can be considered as a combination of a large number of particles, in which all the particles remain at a fixed distance from one another, both before and after applying a load. So this model is important because the body's shape does not change when a load is applied, and so we do not have to consider the type of material from which the body is made. In most cases, the actual deformations occurring in structures, machines, mechanisms, and the like are relatively small, and the rigid body assumption is suitable for analysis. When we are talking about force, so concentrated force represent the effect of a loading which is assumed to act at a point on a body. So we can represent a load by a concentrated force provided the area over which the load is applied is very small compared to the overall size of the body. An example here is the contact force between a wheel and the ground. So steel is a common engineering material that does not deform very much under load, so we can consider this railroad wheel to be a rigid body acted upon the concentrated force of the rail. So one example of the force is point force or concentrated force, but imagine that we have some bridge and you have all these trucks, cars, etc. to be applied. So that is the second type of load also. Or wind can also be a load, or it is a load. Then we have a snow represented as a load. Then we have a self-weight, which can be represented as a distributed load on a construction. So we need to transform this distributed load into concentrated force. So that is the examples of the load which we will cover in this term and in the next videos. So here in statics, we are using 3 Newton's laws of motion. The first law, that a particle originally at rest or moving in a straight line with constant velocity tends to remain in this equilibrium state provided the particle is not subjected to an unbalanced force. So this is the first law. Then we have the second law, which I already mentioned, that force is equal mass times acceleration. So a particle acted upon by an unbalanced force F experiences an acceleration, and that has the same direction as the force and a magnitude that is directly proportional to the force. So the equation, very important. The third law, that the mutual forces of action and reaction between two particles are equal, opposite, and collinear. We have also Newton's law of gravitational attraction. So we have, shortly after formulating his 3 laws of motion, Newton postulated a law governing the gravitational attraction between any two particles. So we have that force is equal universal constant of gravitation, which is given to us as 66.73 times 10 on minus 12 meter cube over kilogram times second on square times mass of one particle times mass of the other particles and r on square, which is the distance between the two particles. We have 2 unit systems. The first one is International System SI, and the second one is US customary system. And using the force is equal mass times acceleration, we will obtain the old units in statics. For gravitation in SI units, we are using 9.81 Newton. And for gravitational force in US customary units, it will be 32.2 pounds. Mass in SI units will be kilo, and in a US system, it will be 1 slug. So we have system of units. The length is meter, time is second, mass is kilogram, and the force is derived unit, which means mass times acceleration, or kilograms times meter over second square, and that unit for us is Newton. In US system, we have length foot time second. Slug is derived for a mass, but force has a unit of pound. So slug will be pound times second square times divided by feet. So this is the units, 4 units, which we will use the most in statics. So there are some rules regarding to the international system of units. So we don't have plurals, we have 5 kilogram, not kilograms. We need to separate units with a dot. Meter second is meter dot second. Most symbols are in lowercase. Key exceptions are Newton, Pascal, mega, and giga. Exponential powers apply to units. For instance, millimeter dot millimeter is millimeter square. Compound prefixes should not be used. We have some prefixes used in the SI units. If we have giga, that is 10 on 9th, and SI symbol will be G. Mega is 10 on 6th, SI symbol is mega or M, capital letter. 10 on 3rd is kilo, SI symbol is K. Then we have milli, SI unit is M, 10 on minus 3rd. Micro, we have 10 on minus 6, nano is 10 on minus 9, and we have a pico, which is 10 on minus 12. Numerical calculations. We must have dimensional homogeneity. Dimensions have to be the same on both sides of the equal signs. Then we have the rules for the rounding numbers. For rounding numbers, suppose the number 3.5587 has to be rounded off to 3 significant figures. Because the 4-digit 8 is greater than 5, the third number is rounded up to 3.56. If we have 0.85896, we will have 0.590. If we have 1.341, then we have, for instance, if we want to round on a 2 significant number, it will be 1.34. And if we have 0.3762, then we will have 0.376, and 9.871 becomes 9.87. So there is one rule if we have number that ends in a 5. If the digit preceding the 5 is an even number, then this digit is not rounded up. If the digit preceding the 5 is an odd number, then it is rounded up. For example, 75.25. Then rounded off to 3 significant digits becomes 75.2. Or if we have 0.1275, it will become 0.128. And if we have 0.2555, it will become 0.256. There are some examples regarding to this chapter. So we need to convert 2 kilometers per hour to meter per second. Since that we have 1 kilometer to be 1000 meter and 1 hour to be 3600 seconds, the factors of conversion are arranged in the following order. So we have 2 kilometers per hour to be 2 kilometers times 1000 meters divided by hour, kilometers, and into second it is 3600 seconds. So we need to divide 2000 meter with 3600 seconds, and our answer is 0.556 meter per second. Or we have one more example. We need to evaluate each of the following and express with SI units having an appropriate prefix. So we have, for the first example, 50 millinewton times 6 giganewton. So 50 millinewton we have for milli prefix time 10 on minus 3 times Newton times 6 giganewton. Giga is 10 on 9 Newton. When we multiply, we will get 300 times 10 on 6 Newton on square. So how much is Newton in kilonewton? So we have 1000 Newton into 1 kilonewton. Since that we have here on square, that means that 1 kilonewton has 10 on 6 Newton square. So our answer is 300 kilonewton square. So that will be the convention. So kilonewton square is 10 on 6 Newton square. If we have to find the answer for 400 millimeters times 0.6 meganewton on square, whole number on square, we have 400 times 10 on minus 3 meter times 0.6 mega is 10 on 6 Newton and everything on square. So that will become 400 times 10 on minus 3 meter times 0.36 10 on 12 Newton square, which will give me the answer 144 times 10 on 9 meter times Newton on square. 10 on 9 meter is gigameter, so the final answer will be 144 gigameter times Newton on square. It's dot Newton on square. So that is one part of solution. We can also write this 144 times 10 on 9 meter times Newton on square is 144 times 10 on 9 meters times Newton on square. And now to divide everything with 10 on 12 meganewton. So that will be our answer. And part C, we have 45 meganewton on cube divided by 900 gigagrams. That is 45 times 10 on 6 Newton, and 10 on 6 Newton will be on cube, and we are dividing by 900 times 10 on 6 kilograms. When we solve this, we will obtain 50 times 10 on Newton, 10 on 9 Newton on cube over kilograms, which will give us the final answer 50 kilonewton on cube over kilograms. So that will be our answer. With this final example, we are done with the part 1.1 to 1.6 in the Hibbeler's books, that is the statics.